Mr. P here. I'm gonna wait a couple seconds because it seems like on this app that I'm using to make this video, always the sound kind of has to kick in 5 seconds in or so. So we should be good now. So some things to remind you of. So first off, you might hear my kids running around in the background. It's Saturday in my world, but in your world, it is Thursday. Okay, so this is Thursday. Remember to remind you to follow at Whiteboard Mr. P on Twitter. Yesterday you guys handed in your Lewis worksheet. I should be able to grade those and get those back. I should have hopefully got them back to you. And then we'll go over the answer key that I sent to you and talk about some of the things that I want to point out. And then today, make sure that you've done your forum check-in, least state name and period, and you must describe one favorite thing you've done during our 2 weeks away for today's check-in. So that's just kind of a fun thing for us to be able to talk and say some things that we've been doing. And then if there's any questions about tomorrow's quiz, right? So tomorrow is the quiz on Lewis structures, and the quiz will be emailed to you at the beginning of your class period, and then it's due by the end of the class period. Just submit it to me in any digital format. Probably easiest just to email me a picture. What else? And I'll be available in the forum tomorrow for responses to any questions that you guys have. As always, reach out to me, emails, whatever, let me know. And then today, primarily, we're going to be talking about, after we go over the worksheet that you guys handed in yesterday, we're going to go through and talk about some exceptions to the octet, expanded octets, and some things to look out for. These items will not be on tomorrow's quiz. So I want to be clear with that. It's not on tomorrow's quiz. The only thing that tomorrow's quiz is writing Lewis structures, just like what you did on the worksheet that you guys completed yesterday, okay? So the stuff that we're gonna be moving into right now is not on the quiz. All right, so let's go ahead and move into, so the worksheet that you guys handed in yesterday, just numbers 1, 2, 3. I'm primarily gonna look at the ones on the front, and we'll talk about some general things about the ones on the ones on the first slide, the covalently bonded substances, and then the color coding with ionically bonded substances, just to have some general things to remind you of. So number one, water, H2O. A lot of you had this as a straight molecule, and that's fine. We're not getting too heavy into some of the structural dynamics, but there is some reasoning behind why this is actually a bent molecule. It goes back to the Lewis structure for the individual atom. Remember, oxygen usually is on the corners like this. So when water forms, it forms the hydrogens that bond to the oxygen that's central are at an angle. And that's going to be part of a conversation that we'll be having in the near future. NH3 right here. Again, big thing. Remember, we're putting those those unshared pairs. CH4, there's the HCl. Double bonds here between the carbon and the two oxygens. 5, 6, 7, 8. This is probably a lot. I know a lot of you will probably end up coming up with this version, which is not wrong, and I'm not going to end up marking it wrong or like that, but excuse me. But the real version is over here that I have depicted right here for O3, which is ozone, and actually it shows resonance. So really you would have to draw two different structures, putting the double bond here and the single bond here, because it has two resonance forms. But again, if you had this, you're not wrong, right? And in kind of reality, the funny thing is that if you calculate like formal charge, this one actually kind of works out better than this one. But I'm telling you that most of the time, ring structures like this, especially with real small molecules, just doesn't happen. So this is the actual structure here for ozone, O3. Then on the back side, I don't have every one drawn up. I've just got a couple that I wanted to point out to you. Remember, no dashes. Careful with your circles. Make sure that you're clearly showing, right, electron ownership of the around the negative ion that now has taken those electrons that were initially owned by the positive ion. Notice, don't make sure that you're not drawing these side by side. In this case, like with number 2, you got to make sure you have magnesium in the middle, right? And the chlorides are on the opposite sides. And that, again, that kind of based is off of primarily magnesium has, the 2 valence electrons. And in drawing the Lewis dot diagram for the individual ion, or I'm sorry, the individual atom, they're side by side. Okay. And then the last thing too, like with number 3 here, and then we'll get moving on to some other things. You'll notice, right, again, that the 2 electrons that calcium gave up to the oxygen to form oxide, those 2 electrons, right, you can't put them on the same side, right? You couldn't put them both on the same side, because again, remember, oxygen is going to have an initial Lewis dot diagram for the unpaired atom looking something like this. You need to place them, like I have it drawn above, in those 2 empty orbitals. Okay, so hopefully that makes sense. Hopefully you guys are okay with that. Like I said, I'm kind of speaking in the future tense right now, so it's a little weird for me, but I think you guys will do fine. And if there's any questions, obviously we'll see you guys in the forum today, or I will have seen you in the forum today. But I wanted to make sure I took some time to look at this. All right, so moving on today, we're going to talk about exceptions to the octet and talk through a little bit on what this means. So as always, as you guys have come to realize in the world of chemistry, there's some nice consistencies, and there's things that work and things that are nice and smooth. And I think that that's one of the attractive pieces about chemistry, at least in my opinion. I've shared this with you guys, but there's a sequence, right? But always, sometimes there's going to be some exceptions, and that's what we're going to be going through today. And primarily what I want to kind of arm you with is think of these exceptions and these sort of warnings that I'm taking you through as kind of light bulbs that go off above your head when you're being asked to create Lewis structures for ones that fit the bill within these different categories. It should be sort of a light bulb or a ding ding ding, an alarm that ends up getting you to take some time with it, right? And you're gonna have to put some thought into it, maybe a little bit more than some of the ones that we would normally experience on the worksheets and the quiz that we're doing tomorrow and stuff like that. So again, this stuff is not on tomorrow's quiz, but let's talk. So some exceptions to the octet. The first is that there are certain situations where there are electron deficiencies. No matter which way that you sort of slice it, you can't distribute the electrons evenly. And this is in scenarios where there are an odd number of valence electrons, okay? So, like for example, NO, nitrous oxide, and nitrogen dioxide. Okay? Nitrous oxide is the stuff that they give you at like the dentist office, the gas at the dentist office. Nitrogen has 5 valence electrons. It's in group 15. Oxygen has 6 valence electrons, right? It's in group 16. So 5 plus 6 is 11. Nitrogen, 5 plus 6 plus 6 is 12. 12 plus 6 is 17. There's no way to evenly distribute the electrons around the Lewis structures that you would have to come up with or propose, because it's an odd number. And we know that these sides represent orbitals. Orbitals want to carry 2 electrons. So we can't distribute it evenly. It's not possible. And this is what happens in nature, right? So as an example, right, here's those 2 that we just talked about. Oxygen has this tendency to want to form 2 bonds, so it'll form a double bond to nitrogen. Nitrogen wants to form 3, but it can only form 2. So it's got this kind of extra electron sort of hanging out here. In the NO2 example, you got to express resonance. There's 2 resonance forms here. Same thing, nitrogen wants to form 3 bonds, right? Which it can in some ways, but then this oxygen's not really super satisfied because it only has 2 bonds. Where do you put all these electrons? There's this sort of extra electron that's hanging out here, right? What's that extra electron? It's called, just for the sake of saying it, they're called free radicals. And I don't know if you guys ever heard, like, eat these specific foods or vegetables or things like that because they're high in antioxidants. They fight free radicals and things like that. What are the different, like, vegetables and vitamins and minerals are considered antioxidants because they will combat and bond with these things called free radicals. Think of them as sometimes like molecular bits almost. As you look at this, it's kind of like we have this orbital that's half filled. Like, nitrogen wants to bond to something. It's going to stick to something. This extra electron is going to want to stick to something or find something else to stick to or bond to. And these types of molecules, you would get the impression, the understanding that, they're pretty reactive, pretty fast working. And remember, I mentioned just a minute ago, this stuff, nitrous oxide, is used in used in dentist offices as a what do they call it? Anesthetic, right? So the gas that you get at the dentist office, if you've ever had that at the dentist office, it's pretty fast acting. Like, if you've ever had this, it's within seconds after you are breathing in this gas for a short period of time, you immediately feel a response of it. And why is it? It's because of this sort of extra electron kind of hanging out, wanting to find something to do. Okay. So these are 2 examples right here, right, that I want to ask you a question about, right? So I'm just going to quickly explain. And it also goes back to our lecture from yesterday, a little bit of practice. I want you to look at what I've proposed to you in these 2 examples. That is 2 electrons there, just to make sure you guys see that. Hopefully you can see this okay. Calculate the formal charge for these 2 options for BEF2 and the 2 options that I've given you for BF3. Pause the video right now and then do that work. Calculate formal charge and then decide which one of these 2 options, option A or option B, or option A or option B, is the correct one for each. And then we'll kind of come back to some discussion of this. So pause the video, pause it right now, and then we'll come back. But obviously, I'm just going to keep going. All right, so the 2 possible structures that you guys were given, if you look at these, right, they both work. They both have kind of the somewhat correct number of electrons. However, there's some problems, right? You have formal charges of -2 and +2 for the atoms involved in structure number 1. And then in structure number 2, though, the good thing is the formal charges are 0, okay? So beryllium is deficient. It doesn't have, an octet to try to fill. It can't. There's a deficiency in terms of its structure, but formal charge has confirmed it. Over here, right? The boron, -1 formal charge. The fluorine, these 2 fluorines would be 0 and 0 here and here, but this fluorine would be a +1. Okay, so the +1, 0, 0. So again, we have bad formal charges here. We got non-zero formal charges, but in this case, again, both in this scenario, structure 2, they're both 0. They're all the fluorines, all the boron are all 0s. So the boron, again, is deficient. Okay, and you'll notice that I put deficient like this at the bottom of the screen. So electron deficient, but some common sense again, though, right? Formal charge calculation tells us these are the correct options. There has to be some common sense, though, if you look at this and understand, right? Here's beryllium and here's boron, right? Beryllium has, 2 valence electrons, right? So boom, boom. So if and when it does form a covalent bond, which again is rare, so you guys understand this. It's only really going to find room to be able to form 2 bonds. Okay. The boron over here, boron's in group 13. It only has 3 valence electrons, right? So there's no way for it to really get to an octet. So it's only going to, when it forms a covalent bond, it's going to bond 3 times. Okay. So the common sense piece that I'm trying to kind of just talk you through is that there's these certain tendencies of based upon their number of valence electrons that they have in the first place. So when I say kind of electron deficient, I mean, they're deficient by kind of the letter of the law, right? This idea of octets versus duets, but are they really deficient, right? Based off of kind of the principles that we've started to understand of how these puzzle pieces fit together. Hopefully that makes sense. I think it does, but you guys will be okay. Let me know if there's any questions on that, but deficiencies. So the big idea here is, again, checking for the number of valence electrons. You got to do that anyway when you're making Lewis structures. If you have an odd number, okay, odd number means, hey, ding, 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 I'm probably going to have some sort of deficiency. This isn't going to fit together perfect. I'm going to have to put some thought into this, okay? All right, now there are expanded octets. So here are a couple of examples, PCl5 and SF6, okay? The central atom has greater than 8 electrons around it. Around this phosphorus here, there's 2, 4, 6, 8, 10 electrons. Around this sulfur here, there's 2, 4, 6, 8, 10, 12 electrons around it, okay? So expanded octets are possible. If you start to play around with maybe some Lewis structures with these, and all of a sudden, you're doing, something that has, like P to Cl to Cl, right, in sequence, right? What are you going to end up having? You're going to have non-zero formal charges. Let's see, 1, 2, 3, 4, 5, boom, and boom. Like if you did some sort of linear sequence in your Lewis structure, rather than this sort of central atom, central atom, phosphorus, and then the chlorines around it, you'd have non-zero formal charges for every one of these chlorines, right? This would be a 0 charge, would be good. The phosphorus, I'd have to figure out. But bottom line is, in this case, it's sort of like, in the sense, think of it sort of as a compromise. You've got phosphorus that's kind of breaking the rules for the purpose of the chlorines to all have the correct number of electrons and to bond the way that they would be expected to bond. Okay, same kind of deal over here with the SF6, right? All of those fluorines, they want to be normal, right? If you start to mess with your, well, it's really raining out. If you start to mess with your bonding pattern, you're going to end up with non-zero formal charges all over the place. Now, so the question is, where do you distribute the extra electrons, right? You distribute the extra electrons around the central atom, okay? So that's where you want to put it. You want to put it around the central atom, okay? All right, so now what I want you to do again is pause the video, and I want you to work on proposing a Lewis structure for XeF4, xeF4, xenon tetrafluoride. This should maybe sort of perk up an interesting sort of piece, because xenon is, hey, it's a noble gas, right? So that's a little weird, okay? So pause the video, guys, and propose it, and then I'm going to keep going though, but pause the video right now and do your structure for xenon tetrafluoride. All right, so you just did example 7.4 in your book. So there's a surplus of electrons, 28 are available, only 24 are required to fill out octets though. The 4 extra electrons are added to the central xenon atom. So again, it's kind of funky. Xenon is a noble gas, and you guys have heard that noble gases don't want to form bonds. Well, sometimes they do. It's very rare, and this is one of those rare situations. Where do where do you put the extra electrons in pairs? You kind of slam them there, slam them in the middle there, right? There's 2 extra pairs of electrons in orbitals surrounding the xenon as the central atom. Okay. So again, just kind of a little note that I have at the bottom. It kind of makes sense. Not going to bust up multiple fluorine atoms would mess up the formal charge because fluorine wants to make one bond. So best option is put them around the Xe, the xenon. But of course, it's a little weird because xenon is a noble gas, like we just talked about. Like I said, we're talking exceptions today, right? The kind of the weirdos of the bunch when we're putting together these different Lewis structures that you may end up encountering. Right? So if this example that you guys just worked on is example 7.4 in your book, so if you go to your textbook, you'll see this exact thing with some more explanation. And then last, just to summarize, and then we're done for the day. To summarize what to look out for, right? So deficiencies, odd number of valence electrons, right? Primarily like nitrogen and oxygen containing molecules. But the number one thing is there an odd number of valence electrons? If it's odd, there's no way to distribute them without being deficient. Deficiencies in a way, you know, like kind of quote unquote deficient, like with the two, if it contains beryllium or boron. Is it truly deficient? Yeah, you can argue that it's maybe not. And then finally, the expanded octets. I think this is a little bit helpful because these are kind of the elements that will show sometimes expanded octets. So in period 3, 4, and 5 in groups 15, 16, 17, and 18. So 3, 4, and 5, 1, 2, 3, 4, and 5 sit kind of in this area. These elements in sort of this area, right? They're kind of the funky ones, right? That will sometimes show expanded octets. It's not a guarantee, right? But they have the potential to show expanded octets beyond what would be expected. And then I kind of put this funky circle around the krypton and xenon. These are like almost like they should be almost dead giveaways, right? Because they're noble gases. Group 18 is the noble gases, and they don't have this tendency to bond. But on the rare occasion that they do, they will form expanded octets. And where do you put those extra electrons? You put them around the central atom. Okay. All right, so that is it for today, guys. Good job. And I will either, depending on when you view this video, I'll either see you in the forum before or after today, right? Make sure that you guys do go to the forum. Okay, and then again, tomorrow is the quiz. So let me know if there's any questions, but quiz tomorrow on Lewis structures. See you guys.